When most people picture the solar system, they picture the planets, the giant worlds, the famous worlds, the ones that fill textbooks, posters, and the imagination. But some of the most violent, mysterious, and scientifically important places in the solar system are not planets at all. They are moons. One moon is pulled so relentlessly by gravity that its surface erupts through hundreds of active volcanoes, making it the most volcanically active world we have ever found. Another hides an immense saltwater ocean beneath a frozen shell, an ocean that may contain more water than every ocean on Earth combined. A tiny moon orbiting Saturn sprays material from that buried ocean directly into space, allowing a spacecraft to taste an unseen sea without ever digging through the ice. One moon has clouds, rain, rivers, lakes, seas, and shifting sand dunes. But the liquid flowing across its surface is not water, it is methane. Another circles Neptune in the wrong direction, moving backward through space as though it never belonged to the planet at all, carrying evidence that it may be a captured survivor from the earliest days of the solar system. Why are so many of the solar system's most active worlds not planets? Why do hidden oceans keep appearing beneath frozen crusts that should be solid to their cores? Why do giant planets often seem calm while the worlds around them carry the real violence? And if life exists anywhere beyond Earth, why are scientists increasingly looking beneath ice instead of beneath open skies? These are not background objects. They are complete worlds with their own histories. Some are burning, some are frozen, some are still changing today. Some may be hiding environments unlike anything we have ever explored. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. Now, let's begin. Long before we could see their landscapes, we learned to arrange the solar system into a simple family. The sun stood at the center. The planets claimed nearly all the attention. Around them drifted smaller companions, drawn as tiny circles that seemed almost decorative beside their enormous hosts. If you grew up with those diagrams, you probably carried the same impression. The planets felt like destinations, the moons felt like footnotes. That picture made perfect sense for centuries. Early telescopes could follow the motions of distant moons across the sky, yet they could reveal almost nothing about the surfaces beneath those tiny points of light. From Earth, they appeared as faint companions with few visible differences. Their individuality remained hidden until spacecraft finally crossed the enormous distances between worlds and began sending close images home. The first great crack in that simple picture appeared in the year 1610. The Italian astronomer Galileo Galilei turned his telescope toward Jupiter and noticed four bright companions changing position from night to night. Those worlds, now known as Io, Europa, Ganymede, and Callisto, were circling Jupiter rather than Earth. It was a profound discovery. Suddenly, Jupiter looked like a miniature planetary system, complete with its own family of orbiting bodies. As our understanding grew, the word moon gained a broader meaning than many people imagine. A moon is simply a natural object that travels around a planet, a dwarf planet, or even a much smaller body elsewhere in the solar system. Some are little more than irregular fragments. Others are covered in ancient craters. Some carry thick ice. Others erupt with lava, hide deep oceans, or hold substantial atmospheres. Their shared name tells us only what they orbit. It says remarkably little about what they truly are. That brings us to another word shaping this journey: terrifying. We are not speaking about monsters or imaginary dangers. We are speaking about overwhelming scale, crushing pressure, violent geology, unfamiliar chemistry, endless darkness, and hidden complexity that challenges our expectations. These places become unsettling because nature itself has built environments unlike anything we experience on Earth. Modern exploration transformed that understanding forever. Robotic spacecraft revealed towering volcanic eruptions, fractured sheets of ice, invisible magnetic fields, enormous impact scars, active plumes, hidden oceans, and atmospheres where few expected them. Every close encounter replaced another assumption with a deeper mystery. We gradually realized these companions were not unfinished versions of planets. They were complete worlds shaped by their own histories, their own internal forces, and their own astonishing evolution. But one moon overturns the old picture faster than any other. Instead of lying frozen and unchanged, it is pulled, squeezed, and heated by gravity until its surface bursts open again and again, turning orbital motion into relentless fire. There is almost no time for a landscape to grow old here. As we turn our attention toward Jupiter's innermost large moon, we find a world whose appearance is rewritten again and again. Every orbit changes it, every cycle leaves fresh scars. Io refuses to settle into permanence. Among every known planet and moon in our solar system, Io holds an extraordinary distinction. It is the most volcanically active world ever observed. Hundreds of volcanoes cover its surface. Some eruptions launch towering fountains of molten material, more than 100 kilometers high, which is about 62 miles, carrying ash and glowing fragments far above the surrounding terrain, before gravity slowly pulls them back. The remarkable part is the source of that energy. Sunlight plays only a minor role. Instead, gravity supplies the power. Jupiter's immense pull continually distorts Io, while the neighboring moons Europa and Ganymede help preserve an orbit that never becomes perfectly circular. That slight stretching matters enormously. As Io moves closer to and farther from Jupiter during each orbit, its shape changes by a small amount. Rock bends, the interior flexes, heat steadily accumulates. Scientists call this process tidal heating. Tidal heating simply means that gravity repeatedly squeezes and relaxes a world until friction inside generates enormous amounts of heat. On Io, that hidden warmth melts rock beneath the crust and feeds relentless volcanic activity. The moon becomes its own furnace, driven by orbital motion rather than internal reserves alone. The result is unlike almost anything else we know. Bright yellow plains spread beside black lava fields. Deep reds blend into orange deposits. White patches mark frozen sulfur compounds. Vast volcanic depressions, called calderas, form where the ground collapses after underground chambers empty. A caldera is a large basin created when the surface sinks into space left behind by erupted material. Across Io, lava flows repeatedly bury older ground, leaving remarkably few ancient impact craters for us to study. Nothing remains unchanged for very long. Fresh deposits blanket older layers. New eruptions reshape familiar regions, even from tremendous distances. Astronomers have watched individual volcanic centers brighten and fade as powerful outbursts transform the landscape once again. If you could somehow stand above this restless world, the greatest danger would come from forces you could never escape. Jupiter is continually pulling on Io. Europa and Ganymede keep that struggle alive through their shared gravitational rhythm. The moon is carried through an endless cycle of stretching and compression that never truly ends. Its orbit has become an engine of geological violence, turning motion itself into heat. For all its extremes, Io offers no evidence of buried oceans or environments considered favorable for life. Its importance lies elsewhere. It reveals how gravity alone can reshape an entire world, proving that distance from the sun, does not always determine whether a landscape remains active. Io is terrifying because it burns, but another moon unsettles us in a very different way, wearing landscapes that almost resemble our own until we discover the flowing liquid is something entirely unfamiliar. Imagine watching clouds gather above a distant horizon, then seeing rain carve valleys, fill rivers, and collect in broad seas. Every part of that scene would feel strangely familiar. As we arrive at Saturn's largest moon, Titan, you might briefly believe you are looking at another version of Earth, shaped by weather and flowing liquids across an active landscape. That first impression does not last. Titan possesses a dense atmosphere, drifting clouds, changing seasons, rolling dunes, winding river channels, expansive lakes, and even seas. Rain falls through its sky. Rivers reshape the ground over immense spans of time, yet the liquid moving through this remarkable cycle is not water. It is primarily methane and ethane, substances that remain liquid in Titan's extraordinary cold. Water behaves very differently here. At the surface, it is as hard as rock, becoming part of mountains and solid terrain rather than flowing across the landscape. The atmosphere deepens that sense of unfamiliarity. Nitrogen makes up most of the air, while a thick orange haze conceals the surface from ordinary view. High above, sunlight interacts with methane molecules, triggering organic chemistry. Organic chemistry simply means chemical reactions involving carbon containing molecules. Those reactions gradually produce increasingly complex substances that drift downward through the atmosphere, coating the landscape with material unlike anything found on Earth. But another puzzle emerges from this chemistry. Sunlight steadily breaks methane apart over time, meaning the gas should slowly disappear from Titan's atmosphere. Observations from the National Aeronautics and Space Administration indicate that some process must be replacing it, yet the ultimate source remains uncertain. Something within Titan continues feeding this remarkable cycle, although scientists have not reached a complete answer. Our closest encounter arrived in the year 2005. The Huygens probe separated from the Cassini spacecraft and descended through Titan's orange veil. During its long fall, it transmitted images revealing branching channels, rounded stones, and a landscape shaped by flowing liquid. After reaching the surface, it continued sending data for more than an hour before contact ended. Humanity had reached one of the most distant landing sites ever explored, discovering a world that looked strangely recognizable while operating according to profoundly different chemistry. As we linger over Titan, its true character gradually comes into focus. This is far more than a small companion circling a giant planet. It possesses its own climate system. Winds sculpt dunes across broad regions. Rain fills lakes and seas. Seasonal changes reshape the environment over time. You begin to recognize a complete world with active processes unfolding across its surface. Yet every familiar feature carries unfamiliar consequences. The rivers cannot sustain terrestrial life. The lakes contain liquids incompatible with human biology. Even the air surrounding the landscape belongs to a chemistry that would overwhelm us almost immediately. Titan reminds us that a world may resemble home while remaining astonishingly foreign. But beneath the frozen shell of another moon, the greatest surprise may lie completely hidden from view. From a distance, Europa seems almost restrained. Light reflects from its icy exterior with remarkable brightness, giving Jupiter's moon an appearance that feels smooth compared with many heavily cratered worlds. Yet as we draw closer, that first impression begins to dissolve. Long reddish-brown bands stretch across the surface in every direction. Ridges rise between fractured plains. Great cracks divide sheets of ice that appear to have shifted, broken apart, and frozen together again over immense spans of time. Those markings tell us that Europa has not remained unchanged. They hint at movement beneath the frozen shell. The surface looks surprisingly young because relatively few large impact craters remain visible. Something has renewed this landscape repeatedly, replacing older terrain with fresher ice and leaving behind a record that is still being interpreted. The greatest discovery, however, cannot be photographed directly. Scientists believe Europa conceals a vast saltwater ocean beneath its icy crust. According to the National Aeronautics and Space Administration, that hidden ocean may contain roughly twice as much water as all of Earth's global ocean combined. We are looking at one of the largest reservoirs of liquid water in the solar system, yet every drop remains concealed beneath an enormous barrier of ice. That hidden arrangement creates a remarkable scientific puzzle. The frozen surface is visible. The ocean below is not. Almost everything that makes Europa compelling exists beyond direct sight. Researchers must rely on careful measurements of gravity, magnetic fields, surface features, and computer models to understand an environment they cannot simply observe with cameras. You will often hear scientists use the word habitability when discussing Europa. Habitability means conditions that could support life as we understand it. It does not mean life has been discovered. It does not confirm living organisms exist there today. Instead, it asks whether the necessary ingredients and environmental conditions might be present within that buried ocean. Several possibilities continue drawing scientific attention. Liquid water appears likely to exist. Chemical ingredients may circulate through the ocean. Interactions between seawater and the rocky interior could provide sources of energy. A young-looking surface also suggests that Europa remains internally active, allowing material and heat to move through the moon over time instead of leaving everything permanently frozen in place. Exploration is now focused on answering those questions with greater precision. In October of the year 2024, the National Aeronautics and Space Administration launched the Europa Clipper mission. Rather than landing immediately, the spacecraft is designed to perform repeated close flybys, studying the ice shell, examining surface composition, measuring the surrounding environment, and evaluating whether Europa possesses environments capable of supporting life as we understand it. For now, Europa continues guarding its greatest secret beneath layers of frozen ice. We can map its surface and measure its surroundings, yet the ocean itself remains beyond our reach. But another icy moon does something almost unbelievable, sending material from its concealed sea outward into space, where passing spacecraft can sample it directly. Some discoveries arrive through patient observation, others burst into view. Enceladus belongs to the second kind. As this small icy moon circles Saturn, it releases material from deep within itself, allowing us to glimpse an unseen interior that would otherwise remain completely concealed. At first glance, Enceladus hardly seems like a world that could transform planetary science. It is much smaller than Titan. It is also far smaller than Ganymede. Its modest size once encouraged the assumption that little could still be happening beneath its frozen crust. But that expectation changed dramatically, and Enceladus became one of the most important ocean worlds ever identified in the solar system. The turning point came during the Cassini mission. As the spacecraft explored Saturn and its moons, it detected towering plumes erupting from long fractures near Enceladus's south pole. Those fractures, sometimes called tiger stripes because of their appearance, continuously vented water vapor and countless icy grains into surrounding space. Careful measurements revealed that this material was rising from a liquid ocean hidden beneath the surface ice. That finding carried remarkable consequences. Scientists did not have to imagine drilling through kilometers of frozen crust, which is about miles of ice that remain beyond present engineering capabilities. Instead, the moon was already delivering samples from its concealed ocean into space. A spacecraft could simply fly through the plume, collect tiny particles, and analyze material that had once been deep below the surface. Few worlds offer such an extraordinary opportunity. As researchers examined those particles, the chemistry became even more compelling. The National Aeronautics and Space Administration reported complex organic molecules, together with tiny rocky particles, carried upward from the ocean system. Organic molecules are carbon containing molecules. They can form through natural chemical processes without any involvement from living organisms. They matter because every known form of life on Earth depends upon carbon based chemistry as one of its fundamental building blocks. Those rocky particles pointed toward another intriguing possibility. Scientists think hydrothermal activity may occur where the hidden ocean meets Enceladus's rocky core. Hydrothermal activity means hot water interacts with rock beneath an ocean, creating chemical reactions that release energy and transform surrounding minerals. Similar environments exist on Earth's ocean floor, where entire ecosystems thrive without relying directly on sunlight. Even with these remarkable discoveries, an important boundary remains firmly in place. Enceladus has never been shown to contain living organisms. No confirmed evidence of extraterrestrial life has emerged from its plumes. What researchers have found are promising ingredients, active chemistry, liquid water, and conditions worthy of careful investigation. Those pieces together make the moon scientifically extraordinary, without allowing conclusions to outrun the evidence. As we continue through Saturn's remarkable family of worlds, Enceladus leaves a lasting impression. Its hidden sea does not remain completely sealed away. It reaches outward into space, sharing fragments of its interior with passing spacecraft. But another moon presents an entirely different mystery, carrying signs that suggest it may never have formed beside the giant planet it circles, becoming instead a traveler captured from somewhere far beyond. Every world carries a history, yet some histories begin somewhere else entirely. Neptune's largest moon, Triton, seems to belong in that remarkable category. Rather than fitting neatly into the orderly picture we often imagine for planetary systems, it hints at an older journey that may have started far beyond the planet it circles today. The first clue lies in the direction of its orbit. Triton travels around Neptune opposite the planet's own rotation. Astronomers describe this as a retrograde orbit. A retrograde orbit simply means a moon moves in the reverse direction compared with the spin of the world it orbits. That detail may sound subtle, yet it changes everything about Triton's story. Most large moons are expected to form from the same swirling material that surrounded their parent planet during its earliest history. Because they form together, they usually travel in roughly the same direction as the planet's rotation. Triton breaks that expectation completely. Its backward path strongly suggests it did not form beside Neptune at all. The leading scientific explanation is both elegant and dramatic. Researchers widely think Triton began life as an independent object in the distant outer solar system, possibly belonging to the same broad population as Pluto and other icy bodies beyond Neptune. At some point in the distant past, Neptune's powerful gravity captured it. Exactly how that capture occurred remains an active area of research, but the evidence increasingly points toward a world that became part of an entirely different planetary family. Such an event would not have been gentle. Capturing a moon as large as Triton requires enormous exchanges of energy. During that process, earlier moons orbiting Neptune could have been destabilized, pushed into new paths, shattered by collisions, or even lost completely. Triton's arrival may have rewritten the architecture of the entire system, leaving us with only fragments of what once existed. Our closest look came in the year 1989, when Voyager 2 swept past Neptune and Triton during humanity's only spacecraft visit to that distant region. Images returned to Earth revealed an icy landscape that appeared surprisingly youthful. Broad frozen plains stretched across the surface. Unusual terrain resisted simple explanation. Dark streaks extended across the ice, suggesting material had erupted and settled back onto the ground. Observations also confirmed a thin atmosphere composed mainly of nitrogen, an unexpected feature for such a remote world. Those discoveries transformed Triton from an overlooked companion into one of the solar system's most intriguing objects. Instead of resembling an ordinary moon shaped entirely by Neptune, it feels like a preserved relic carried in from another neighborhood of the Sunday. You are looking at a world that may have spent part of its existence somewhere else before becoming permanently bound to a blue giant. Triton carries the feeling of something displaced, a traveler whose path changed forever through gravity alone. But appearances can deceive in another direction as well. One small moon seems cold, battered, and inactive, although recent evidence suggests its hidden interior may tell a very different story. One enormous scar defines almost everything you notice at first. Across the face of Saturn's small moon Mimas, a colossal impact crater known as Herschel dominates the landscape so completely that it has shaped the moon's public identity for decades. Its rim rises high above the surrounding plains, while its central peak climbs from the crater floor like a mountain born from catastrophe. The collision that created it came astonishingly close to breaking the entire moon apart. That overwhelming crater encouraged a straightforward conclusion. Mimas appeared small, icy, heavily cratered, and largely unchanged across immense spans of time. Unlike Enceladus, no dramatic plumes streamed into space. Unlike Titan, no thick atmosphere softened the horizon or supported weather. Images returned by visiting spacecraft seemed to show a world preserving ancient damage rather than creating anything new beneath its frozen exterior. For many years, that interpretation remained convincing. Mimas looked like a body whose most important events belonged to the distant past. Its battered appearance fit comfortably into familiar expectations about small moons, where limited size suggested limited internal activity. Surface observations offered little reason to imagine anything more complicated hidden below the ice. But scientific understanding rarely depends upon appearance alone. Recent research has suggested that Mimas may contain a comparatively young ocean beneath its icy shell. This possibility emerged from detailed studies of the moon's motion and subtle changes in its rotation, observations that can reveal information about structures concealed deep inside a world. The idea remains under active investigation, yet it has already transformed the questions scientists ask about this seemingly ordinary moon. If that hidden ocean truly exists, its implications reach far beyond Mimas itself. A frozen exterior no longer guarantees a frozen interior. Geological activity may continue where no obvious surface evidence announces its presence. Layers of ice can conceal environments that escape detection until increasingly precise measurements reveal unexpected clues. Suddenly, Outward appearance becomes a far less reliable guide than once believed. That distinction deserves careful attention. Researchers have not declared the presence of an underground ocean to be an established certainty. Current evidence supports a compelling scientific possibility rather than a final conclusion. Future observations and additional missions will continue testing this interpretation, refining our understanding of what lies beneath the fractured shell. Even so, Mimas has already changed the conversation. It demonstrates how easily the solar system can overturn assumptions formed through distant observation alone. We may look directly at a heavily cratered world and still misunderstand its present condition. Beneath an ancient face, internal evolution may continue beyond the reach of ordinary cameras. As you consider Mimas, the unsettling thought is difficult to ignore. A moon that seemed frozen in history may still be changing from within, carrying a concealed ocean beneath scars billions of years old. But the next destination expands the scale dramatically, introducing a world larger than the planet Mercury, remarkable enough to generate its own magnetic field while remaining a moon. Size alone can overturn familiar categories. As we arrive at Ganymede, Jupiter's largest moon, the distinction between planet and moon begins to feel less meaningful than it once did. This immense world refuses to fit comfortably inside the label it has carried for billions of years. Ganymede is the largest moon in the entire solar system. Its diameter exceeds that of the planet Mercury, an astonishing comparison that surprises many people encountering it for the first time. Yet, diameter tells only part of the story. Mercury remains more massive because it is denser, containing a much larger proportion of heavy rock and metal. Ganymede includes substantial amounts of ice along with rock, giving it tremendous size without matching Mercury's overall mass. Even that remarkable scale is not its greatest surprise. Ganymede is the only known moon capable of generating its own magnetic field. A magnetic field is an invisible region created by motion inside a world, usually involving electrically conducting material deep beneath the surface. On Earth, our magnetic field guides the movement of charged particles arriving from space and helps shield the planet from much of the incoming radiation carried by the solar wind. For Ganymede, that achievement becomes even more extraordinary because it exists within Jupiter's enormous magnetic environment. Instead of being completely overwhelmed by the giant planet surrounding it, Ganymede maintains its own smaller magnetic bubble nested inside Jupiter's far larger one. Few places in the solar system demonstrate such a layered interaction between magnetic environments, making the moon an exceptional natural laboratory for understanding planetary interiors. Its surface tells an equally intricate story. Broad, dark regions preserve some of the oldest terrain visible on the moon, recording events from the distant past. Crossing those ancient landscapes are brighter grooved bands that stretch for great distances, suggesting episodes of crustal movement and geological change. Rather than displaying one consistent appearance, Ganymede preserves evidence from different chapters of its evolution, each layer revealing another stage in a history spanning billions of years. Scientists also continue gathering evidence that another hidden ocean may exist beneath the frozen exterior. One important clue comes from observations of Ganymede's auroras. Auroras are glowing patterns created when charged particles interact with a magnetic environment. Careful studies of how those auroras behave have strengthened the case for a salty subsurface ocean because electrically conducting salt water could influence the moon's magnetic response in measurable ways. You may notice that Ganymede inspires a different kind of unease than the worlds we have already visited. Explosive volcanoes do not define it. Towering plumes do not dominate its identity. Instead, it steadily dissolves the assumption that a moon must always be smaller, simpler, or less capable than a planet. It expands the category until the word itself seems inadequate. Ganymede stands as an immense and internally complex world, whose true nature extends far beyond its title. But the next destination follows an opposite path, preserving an ancient phase where countless impacts still record the earliest violence of the solar system. If some worlds are defined by change, others are defined by endurance. Far beyond Jupiter's restless inner moon's travels, Callisto, the outermost of the four large moons, first observed by Galileo Galilei. It does not draw attention through towering eruptions or hidden plumes. Instead, it offers something far rarer, a landscape that has preserved an extraordinary record of the distant past. At first glance, Callisto appears dark, icy, and heavily scarred. Its surface lacks the broad, smooth plains seen elsewhere in the Jovian system. Ancient impact features overlap one another until individual events become difficult to separate. Everywhere you look, another crater interrupts the terrain, creating a world whose appearance has changed surprisingly little across immense stretches of time. Scientists consider Callisto's exterior to be among the oldest and most heavily cratered surfaces anywhere in the solar system. That distinction carries tremendous importance. Many active worlds gradually erase evidence of their earliest history. Volcanoes spread fresh material across older ground. Weather slowly reshapes exposed landscapes where atmospheres exist. Plate tectonics, the slow movement and recycling of large pieces of a planetary crust, continually transforms Earth's surface. Those processes remove ancient records as new geology replaces the old. Callisto followed another path. It experienced very little large-scale resurfacing, allowing impact scars to remain visible instead of disappearing beneath younger terrain. The result resembles an archive written directly onto ice and rock. Every preserved crater contributes another page to a story extending back toward the earliest chapters of solar system history. As we drift above this remarkable moon, the view becomes almost overwhelming. Crater follows crater across the horizon. Bright rings stand out against darker frozen ground. Enormous impact basins spread across vast regions, while countless smaller collisions fill nearly every remaining space. Rather than appearing chaotic, the landscape feels like accumulated memory, each mark surviving because so little arrived afterward to erase it. Those preserved scars reveal much more than the locations of ancient collisions. Scientists study crater populations to estimate the relative ages of different regions. Relative age means determining whether one surface formed before or after another without assigning an exact number of years. The abundance and distribution of impacts also reveal how intensely the early solar system was bombarded, while showing that Callisto experienced remarkably little geological renewal after those violent beginnings. You may notice that Callisto inspires a different kind of fascination from the worlds we have already visited. It does not astonish through ongoing activity. Instead, it reminds us how much history can survive when almost nothing disturbs the surface for billions of years. Every preserved impact becomes evidence that the young solar system was a far more dangerous place than the orderly arrangement we observe today. Callisto demonstrates what happens when a moon remembers nearly everything. Its frozen exterior has become a lasting record of ancient violence. From here, our attention gradually shifts away from individual worlds and toward the deeper gravitational forces that shape entire moon systems, driving many of the remarkable extremes we have encountered along this journey. After meeting so many extraordinary worlds, a deeper pattern begins to emerge. None of these moons exists in isolation. Every one belongs to a larger gravitational family, where invisible forces constantly shape motion, internal structure, and geological history. Their remarkable differences are often connected by the same unseen influence. The giant planets stand at the center of these systems. Jupiter, Saturn, Uranus, and Neptune possess immense masses, allowing their gravity to reach far beyond their visible clouds. That pull does far more than keep moons in orbit. Over immense spans of time, it can alter orbital paths, stretch planetary interiors, and influence whether a distant world remains frozen or surprisingly active. But gravity becomes even more powerful when multiple moons interact. Scientists describe one important process as orbital resonance. Orbital resonance is a repeating gravitational rhythm in which the orbits of two or more moons line up in a predictable pattern. Each close alignment delivers another carefully timed gravitational tug, preventing the system from settling into a perfectly stable arrangement. Jupiter provides one of the clearest examples. Io, Europa, and Ganymede remain linked through this repeating relationship. Every orbit helps preserve the next, maintaining a delicate balance that has endured for extraordinary lengths of time. Instead of allowing Io's path around Jupiter to become perfectly circular, those repeated interactions continually restore a slight distortion. That distortion introduces another important idea: eccentricity. Orbital eccentricity simply means an orbit is not a perfect circle. A moon following such a path moves through slightly changing distances as it travels around its planet. Those changes may appear modest on astronomical scales, yet they produce powerful differences in gravitational force from one part of the orbit to another. As Io completes each journey around Jupiter, the changing pull gently reshapes the entire moon. Rock compresses, rock relaxes. The process repeats again and again without interruption. Friction develops deep below the surface as solid material continually flexes. Over time, that friction generates enormous quantities of heat hidden beneath the crust. The consequences extend far beyond volcanic eruptions alone. Internal warming can fracture frozen shells, reshape landscapes, and help preserve liquid oceans beneath thick layers of ice. A moon may appear cold from space while remaining surprisingly active below its surface, sustained by energy that arrives through gravity rather than direct sunlight. The engine remains invisible, yet its effects become unmistakable once we recognize the pattern. You can begin tracing that pattern across many of the worlds we have already encountered. Some respond with flowing lava, others preserve concealed seas, still others reveal fractured crusts or changing interiors. Although their appearances differ dramatically, the same fundamental force often lies beneath those differences, steadily transferring orbital motion into internal heat. This realization reshapes one of the oldest assumptions about distant worlds. Warmth does not always depend upon closeness to the sunday. Gravity itself can become a long-lasting energy source, sustaining environments where earlier generations of scientists expected only permanent ice. With that understanding, the possible locations of hidden oceans expand far beyond the boundaries once imagined. For a long time, distance seemed to provide a simple answer. Travel far enough from the sun, and warmth should disappear. Oceans should freeze solid. Geological activity should fade away. The outer solar system appeared destined to become a collection of cold, inactive worlds where little could continue changing beneath the ice. Yet, nature proved far more inventive than that familiar picture suggested. As spacecraft returned increasingly detailed observations, scientists found compelling evidence that frozen surfaces do not always reveal frozen interiors. A thick shell of ice can conceal an environment shaped by processes that continue long after sunlight has weakened into a faint glow. One important reason is surprisingly familiar. Ice does more than preserve cold. It also acts as insulation, slowing the escape of heat from deep below the surface. When warmth becomes trapped beneath many layers of frozen material, it can remain there across astonishing spans of time. An icy crust that appears lifeless from above may actually help protect a liquid ocean hidden far beneath it. Chemistry also plays a significant role. Dissolved salts or substances such as ammonia can lower the freezing point of water, allowing liquid reservoirs to survive under conditions where pure water would become solid. Combined with internal sources of heat, those chemical effects make underground oceans much more stable than earlier generations of scientists once imagined. Another source of warmth comes from radioactive decay. Radioactive decay is the natural process in which certain elements gradually change into different elements while releasing energy as heat. Deep inside rocky interiors, that slow release can continue for billions of years, providing an additional contribution to the thermal balance of a moon. The process is gentle, yet its effects accumulate across immense stretches of time. Gravity strengthens that picture even further. As we have already seen, tidal heating, generated through repeated gravitational stretching, can continue warming an interior long after the surrounding environment has become intensely cold. Several different processes, therefore, work together rather than relying upon a single source of energy. Heat may arrive from radioactive decay, remain trapped beneath insulating ice, while gravity continually adds more energy from the outside. These hidden oceans matter for another reason as well. They do not depend directly upon sunlight to remain liquid. Thick ice shields them from much of the intense radiation striking exposed surfaces around giant planets. The environments below may therefore remain comparatively stable, while the landscape above experiences conditions that appear entirely hostile. A remarkable pattern gradually emerges from these discoveries. Europa belongs within it. So does Enceladus. Ganymede joins the list through growing evidence of its concealed sea. Titan may also harbor liquid water beneath its frozen shell, despite the unfamiliar chemistry at its surface. Even Mimas has entered the discussion through recent research, suggesting that appearances alone can be deeply misleading. You begin to realize that oceans may be far more common than visible seas. They simply occupy places hidden beneath layers of ice instead of open skies. Once that possibility becomes part of our understanding, another question naturally follows. If these concealed oceans truly exist, what kinds of chemistry might be waiting within their unseen depths? Habitability takes on a different meaning once we descend beneath frozen shells. It does not mean life has been discovered. It describes a collection of conditions that could allow life to emerge or survive. As we continue this journey, you begin to see that scientists are searching for a checklist rather than a conclusion. Liquid water stands near the top of that list. Water allows molecules to move, react, and combine in ways that support complex chemistry. But water alone cannot complete the picture. Chemical building blocks are equally important. Carbon-containing molecules, along with other essential elements, provide the raw materials from which more elaborate structures may develop. Energy must also be available because every known living system requires a continuing source of power to maintain itself. Time matters as well. Chemical processes capable of increasing in complexity often require immense stretches of time, unfolding over millions or even billions of years inside environments that remain comparatively stable. One part of this checklist surprises many people. Life does not necessarily depend upon sunlight shining directly into an ocean. Here on Earth, certain ecosystems flourish far below the reach of daylight by relying upon chemical energy instead. Chemical energy is energy released when substances react with one another. Some organisms obtain that energy from reactions involving rocks and water rather than from sunlight, demonstrating that different paths can sustain living systems. That possibility draws scientists toward places where water meets stone beneath an icy crust. When liquid water comes into contact with a rocky seafloor, chemical reactions can occur between minerals and the surrounding ocean. Those reactions may create energy gradients, meaning regions where energy naturally flows from one chemical state to another. Such gradients can provide opportunities for increasingly complex chemistry to continue over very long periods. But the presence of these reactions alone tells us nothing about whether biology has ever appeared. This is one reason plumes receive so much scientific attention. When material rises naturally from an underground ocean into space, it offers a rare opportunity to examine a hidden environment without tunneling through kilometers of ice, which is about 621 miles. Tiny grains, water vapor, and dissolved chemicals can carry clues about the unseen ocean below. By flying carefully through those expanding streams, spacecraft can analyze their composition and reconstruct part of the chemistry occurring deep beneath the frozen exterior. Still, every promising discovery requires careful restraint. Ingredients are not organisms. Chemistry is not biology. A location that appears favorable for life remains only a candidate until direct evidence exists. Each observation narrows the possibilities while leaving room for uncertainty, reminding us that the strongest scientific conclusions emerge through patient testing rather than hopeful assumptions. But every new clue also raises an equally important responsibility. Once we identify places that may possess the conditions for life, we must decide how to explore them without changing the very environments we hope to understand. Long before a spacecraft ever approaches an icy moon, another journey has already begun. Engineers and scientists spend years preparing a machine that must travel across the solar system while carrying as little of Earth with it as possible. Every bolt, instrument, and surface becomes part of a careful effort to prevent an unintended visitor from making the trip alongside us. This effort is known as planetary protection. Planetary protection is a collection of rules and scientific practices designed to avoid contaminating other worlds with life from Earth, while also protecting Earth from potential materials returned by future missions. It exists because exploration is no longer only about reaching distant places. It is also about preserving them well enough that the answers we discover remain trustworthy. That responsibility becomes especially important around icy moons believed to contain hidden oceans. If a world may possess environments capable of supporting life as we understand it, then every spacecraft must be cleaned with extraordinary care before launch. Even microscopic organisms that survive on Earth could complicate future investigations. Should those organisms somehow reach another world, scientists might later mistake their chemical traces for evidence of native life. A remarkable discovery could become impossible to interpret with confidence. Europa and Enceladus stand among the clearest examples of this challenge. Their concealed oceans have transformed them into places of exceptional scientific value. We have already seen that these hidden seas may contain water, chemical ingredients, and sources of internal energy. But those same possibilities demand greater caution whenever humanity plans a mission. The more promising a destination appears, the more carefully we must approach it. Scientists describe one concern as forward contamination. Forward contamination means Earth organisms are accidentally carried to another world. Although spacecraft are assembled under carefully controlled conditions, complete sterility is extraordinarily difficult to achieve. Every mission, therefore, seeks to reduce biological contamination to the lowest practical level before leaving our planet. There is another side to this responsibility as well. It is called backward contamination. Backward contamination refers to the careful handling of extraterrestrial material that might someday be returned to Earth. No mission has yet brought samples from the hidden oceans beneath these icy moons, yet researchers already plan for that possibility. Any future material would be studied under strict containment until its properties were thoroughly understood. This careful balance shapes the story of exploration itself. We often imagine discovery as moving faster, traveling farther, and reaching every destination as quickly as possible. But these distant oceans ask something different of us. They remind us that patience can protect knowledge. Rushing ahead may satisfy curiosity for a moment, yet it could damage the very environments we hope to understand for generations. But restraint also gives every successful encounter greater meaning. Each spacecraft that has crossed these distant systems carried only a brief opportunity to observe, measure, and listen before continuing into the darkness, leaving behind discoveries that continue to guide us long after the encounter itself had ended. Our understanding of distant moons did not change all at once. It changed each time another spacecraft crossed the darkness and replaced a point of light with a place. Every close encounter revealed landscapes that no telescope on Earth could fully uncover, turning distant companions of giant planets into worlds with their own histories. The Voyager missions marked the beginning of that transformation. Voyager 1 and Voyager 2 swept through the outer solar system and forever changed how we viewed planetary moons. Their cameras revealed that these distant bodies were far more than frozen spheres circling larger worlds. We saw the erupting surface of Io, unexpected icy landscapes, and the remarkable complexity surrounding the giant planets. Moons that once seemed interchangeable immediately became distinct places with different stories written across their surfaces. But the questions multiplied even faster than the answers. The Galileo spacecraft entered orbit around Jupiter during the 1990s and continued exploring into the early years of the 21st century. Repeated encounters with Jupiter's largest moons provided an entirely different level of understanding. Instead of brief snapshots, Galileo watched these worlds over many years. Evidence accumulated for hidden oceans, active interiors, and complicated geological histories, showing that Jupiter's moons formed an interconnected system shaped by gravity as much as by time. Saturn received an equally remarkable visitor. The Cassini mission remained in orbit around the ringed planet for 13 years, allowing scientists to observe seasonal changes and revisit its diverse collection of moons again and again. Alongside, it traveled the Huygens probe, which descended through Titan's thick atmosphere before landing on its remarkable surface. Cassini also flew directly through the towering plumes escaping from Enceladus, collecting samples that transformed ideas about hidden oceans and the chemistry beneath frozen crusts. More recently, the Juno spacecraft has continued expanding that story. Although its primary mission focuses on Jupiter itself, the mission has been extended to include close observations of several Jovian moons. Each pass has added fresh measurements of surfaces, magnetic environments, and geological features, connecting earlier discoveries with modern instruments capable of greater precision. But exploration has not slowed. The National Aeronautics and Space Administration launched Europa Clipper to investigate whether Europa possesses environments that could support life as we understand it. Through repeated flybys rather than a landing, the spacecraft will examine the moon's icy shell, hidden ocean, and surrounding environment with extraordinary detail. At nearly the same time, the European Space Agency launched the Jupiter Icy Moons Explorer mission, designed to explore Jupiter's icy moons with particular attention devoted to Ganymede and its remarkable internal structure. Viewed together, these missions tell a larger story than any single spacecraft could reveal. Each one contributed another chapter, another measurement, another unexpected discovery. But together they showed that moon systems are not random collections of frozen companions drifting around giant planets. They are families of worlds, connected through gravity, shaped by shared violence, and still evolving long after their formation. Imagine stepping back far enough that a giant planet and its companions become a single picture. Instead of isolated moons scattered through space, you begin to recognize a smaller version of something familiar. Multiple worlds circle one dominant body. Their paths remain connected through gravity, and their histories become woven together across billions of years. Gravity is the thread holding that picture together. Every moon feels the pull of its planet, while neighboring moons influence one another through repeated encounters. Their positions are not random. Their distances matter. Their motions shape one another over immense spans of time, gradually producing very different worlds, even within the same planetary family. Jupiter offers one of the clearest examples. Its four large Galilean moons are arranged in a sequence that tells an extraordinary story. Closest to Jupiter lies Io, where relentless tidal forces maintain extraordinary volcanic activity. Farther outward waits Europa, whose frozen exterior conceals one of the most compelling ocean candidates in the solar system. Beyond Europa stands Ganymede, remarkable for its immense size, complex interior, and magnetic field unlike that of any other known moon. Still farther away circles Callisto, preserving an ancient landscape that has changed comparatively little since the early history of the solar system. Each world reflects its own environment, yet everyone belongs to the same gravitational family. Saturn presents another remarkable collection. Titan surrounds itself with a thick atmosphere and an active weather cycle unlike any other moon. Enceladus releases material from a hidden ocean into space through towering plumes. Iapetus appears almost divided into two different worlds, with one hemisphere dramatically darker than the other. Mimas seems ordinary at first glance, yet recent evidence suggests its interior may conceal far more than its battered surface reveals. Each moon contributes a different chapter, while the planet at the center binds them into a larger story. Seeing these relationships changes how we remember them. You stop thinking about individual names on separate lists. Instead, you begin to recognize patterns across an entire system. One moon influences another. One orbit helps shape another orbit. A discovery made on one world often changes how scientists interpret observations elsewhere. The family becomes easier to understand than the individuals alone. But location also determines the physical forces acting upon each moon. Distance from the planet can influence exposure to intense radiation, the strength of tidal heating, and the long evolution of an orbit. Even modest differences in position may produce dramatically different outcomes over billions of years. A moon closer to its planet may experience continual internal heating, while another farther away preserves ancient surfaces with comparatively little change. The architecture of the system becomes part of every world's identity. As we continue this journey, these moon systems begin to feel less like collections of companions and more like carefully balanced celestial neighborhoods, each shaped by gravity across unimaginable spans of time. But living close to a giant planet carries another consequence. Many of these worlds spend every moment inside vast, invisible storms that never stop surrounding them. Long before you could ever touch Jupiter itself, you would already be traveling through one of the largest invisible structures in the solar system. Surrounding the giant planet stretches its magnetosphere, a vast region controlled by Jupiter's magnetic field. This unseen domain extends millions of kilometers, which is about millions of miles, although its exact size changes as it responds to the ever-changing flow of the solar wind. It reaches far beyond the planet, enclosing many of its moons inside an environment unlike anything around Earth. A magnetic field is an invisible region created by motion within a world. Around Jupiter, that field traps charged particles, tiny particles carrying electric charge, including electrons and ions. Rather than escaping into space, many of these particles spiral along magnetic pathways, racing through the system at tremendous speeds. You cannot see them, yet they are constantly moving. But this invisible activity has real consequences. Charged particles can gradually damage spacecraft electronics, interfere with sensitive instruments, and shorten the working lives of missions that venture too deeply into Jupiter's surroundings. Engineers must carefully design shielding and flight paths because surviving the environment becomes almost as important as collecting scientific observations. These energetic particles also reshape the moons themselves. As they strike frozen surfaces, they trigger chemical changes that slowly transform the uppermost layers of ice. Molecules are broken apart. New compounds form. Over immense spans of time, the chemistry visible from orbit may differ from the chemistry hidden farther below. Scientists therefore examine every observation with care, asking whether a substance originated within the moon or resulted from relentless exposure to radiation. Io contributes to this remarkable system in another way. Material escaping from that restless moon becomes ionized, meaning atoms lose or gain electrical charge and become charged particles. Those particles help supply a vast ring of plasma, an extremely hot gas containing freely moving, charged particles that circles Jupiter. The giant planet continually gathers and accelerates this material, strengthening the complex environment surrounding its inner moons. Europa travels through this energetic region every orbit. Its icy exterior receives continual radiation, leaving chemical fingerprints across the surface. When scientists detect intriguing compounds there, they must carefully separate the effects of surface bombardment from material that may have risen from the hidden ocean beneath the ice. Every measurement becomes a puzzle with more than one possible explanation. But perhaps the most unsettling realization is how little of this activity is visible. A landscape can appear motionless beneath distant sunlight. Nothing seems to move. Nothing appears dangerous. Yet every exposed grain of ice is being struck by invisible streams of energy every moment. The stillness belongs only to the eye. The environment itself remains intensely active, shaped by forces that never pause. As we continue through these distant systems, another process demands equal attention. Radiation transforms, surfaces gradually from above. Impacts reshape worlds from beyond their orbits, sometimes through a single catastrophic collision that changes everything forever. Imagine holding a small icy moon in your hands. Now imagine a collision powerful enough to carve a crater across much of its face, without completely destroying the world itself. Throughout the outer solar system, many moons preserve these ancient impacts because so little erases them. They possess little or no atmosphere. They have no falling rain, no flowing rivers, and almost no wind to soften their landscapes. Many also lack the geological activity that would otherwise bury old scars beneath younger terrain. Because these worlds change so slowly, every major collision becomes part of their identity. A crater can remain visible for billions of years, surviving almost unchanged, while planets elsewhere continually rewrite their histories. We are looking at records that endured because the pages were never turned. Mimas offers one of the clearest examples. Earlier, we met its enormous Herschel crater, but its deeper significance lies in simple physics. For a moon of such modest size, a single impact approached the limit of survival. The crater dominates the body because the body itself is so small. Instead of becoming one feature among many, the collision became the defining characteristic of the entire world. The shock waves likely traveled through much of the interior, revealing that even a comparatively small moon can withstand astonishing forces before reaching the point of destruction. Saturn's moon Tethys tells a related story. Across much of one hemisphere stretches the immense Odysseus crater, another reminder that giant impacts shaped these distant worlds. Despite its tremendous size, the crater appears shallower than scientists once expected. That gentle appearance suggests the icy crust slowly relaxed after the collision, gradually softening its original shape while preserving the overall record of the event. Even damaged ice can change over immense spans of time. Farther outward, Rhea and several other cratered Saturnian moons preserve layer upon layer of collisions. Newer impacts overlap older ones. Smaller craters rest inside larger basins. Every overlapping circle records another chapter in the long history of wandering debris that once filled the young solar system. Looking across these surfaces resembles reading an archive written with impacts instead of ink. But these scars reveal far more than the violence itself. The size and shape of a crater helps scientists estimate the strength of the surface beneath it. The way materials spread after impact offers clues about internal structure. Crater counts across different regions allow researchers to estimate the relative ages of landscapes, revealing which terrains formed earlier and which changed later. Together, these records also preserve evidence of how crowded and hazardous the early solar system once was. Perhaps that is the deepest impression these moons leave behind. They are unsettling through endurance rather than eruption. They survived collisions that nearly erased them, carrying those wounds across billions of years until we finally arrived to notice them. Survival can leave scars. But some moons look strange not because of craters, but because their surfaces seem rearranged from within. Some worlds reveal their history through orderly patterns. Miranda seems to do the opposite. As we arrive at this small moon of Uranus, familiar expectations begin to fade. Instead of presenting one consistent landscape, Miranda confronts you with a surface that appears assembled from different stories, each preserved beside the next, without blending into a single, comfortable picture. Its unusual appearance became widely known after Voyager 2 swept past the Uranus system in 1986. During that brief encounter, the spacecraft transformed a distant point of light into one of the most puzzling landscapes ever photographed. Rather than showing an evenly cratered moon, the images revealed a remarkable patchwork of contrasting terrains that immediately challenged simple explanations. Across Miranda, broad grooved regions interrupt older cratered plains. Enormous canyons slice through the crust, while towering cliffs separate neighboring landscapes that seem to belong to different chapters of geological history. Ancient surfaces marked by countless impacts stand beside areas that appear comparatively younger, suggesting that some parts of the moon experienced significant change long after others had settled into place. The contrast feels almost abrupt, as though separate pieces of a forgotten world had somehow been joined together. Among its most remarkable landmarks is Verona Rupus, a vast scarp, meaning a steep cliff formed where the surface has broken or shifted. It is often discussed as one of the tallest known cliffs in the solar system. Scientists continue to refine estimates of its full height, so its exact dimensions remain an active subject of study. Even with that uncertainty, the scale alone reminds us that Miranda has experienced extraordinary forces capable of reshaping an entire moon. But what produced such an unusual landscape remains an open scientific question. One possibility involves past tidal heating, the internal warming created when changing gravitational forces repeatedly flex a moon. If Miranda once followed a different orbit, those stresses could have softened its interior and driven geological change. Internal deformation, meaning the slow reshaping of material beneath the surface, may also have contributed as layers shifted over immense spans of time. Tectonic activity, the movement and fracturing of the crust, offers another explanation for its striking grooves and cliffs. Large impacts cannot be dismissed either, since powerful collisions may have fractured or reorganized portions of the moon before later processes altered the damaged terrain. Each explanation accounts for part of the evidence. None answers every question. That uncertainty has endured because humanity has seen Miranda only once at close range. Every interpretation still depends upon the limited observations gathered during a single flyby. Perhaps that is what makes Miranda so memorable. It does not resemble a world that simply grew old beneath distant sunlight. It appears disturbed, rearranged, and resistant to any single explanation. We are left studying fragments of a story that remains incomplete. Miranda is only one member of a larger mystery, because the moons of Uranus have barely been visited at all. Beyond Saturn, our journey reaches a planetary system that still feels only partly introduced. Around Uranus travel 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Together they form a family of icy worlds with distinct appearances and histories, yet each remains far less familiar than the large moons orbiting Jupiter or Saturn. What we know is valuable. What we do not know is even greater. Much of that uncertainty comes from a single, remarkable event. In 1986, Voyager 2 swept through the Uranus system during a brief flyby, collecting images and measurements that transformed distant points of light into recognizable worlds. The encounter changed planetary science forever, but it was also fleeting. No spacecraft has ever entered orbit around Uranus, returning again and again to observe changing conditions or examine these moons in greater detail. Since that historic visit, the system has waited without another close exploration. But Uranus itself makes this family especially unusual. The planet rotates on its side, tilted so dramatically that its seasons and geometry differ from those of every other giant planet. Its moons circle within that tilted system, sharing an orbital arrangement unlike anything else among the major planets. Their long histories unfolded under conditions that challenge familiar expectations, making them especially valuable for understanding how planetary systems evolve. Scientists continue studying these moons because each may preserve different pieces of a much larger story. Miranda already hints at dramatic internal change. Ariel displays broad networks of valleys and smoother regions that suggest geological activity in the distant past. Umbriel appears darker and more heavily cratered, preserving an older face. Titania, the largest moon of Uranus, contains extensive fault valleys where the crust seems to have stretched apart. Oberon, the outermost of the five major moons, carries ancient impact scars while remaining one of the least explored large worlds in the solar system. Together, they offer clues about buried oceans, colossal impacts, frozen interiors, and the early history of the outer solar system. Yet every conclusion must remain measured. The available observations are limited. Many features appear only in images captured from a single viewing angle. Large portions of several moons were never photographed in high detail. Important questions about their interiors, geological histories, and possible hidden oceans remain unanswered because the necessary evidence simply does not exist yet. Perhaps that is what gives the Uranian system its distinctive character. These worlds are not unsettling because they have revealed every secret. They are unsettling because one brief encounter remains almost everything humanity has ever seen. Entire landscapes, hidden interiors, and untold histories continue circling a distant planet, with scarcely another visitor to witness them. But even Uranus does not mark the edge of our journey. Far beyond waits Neptune, where its largest moon reminds us that worlds are not always born where we find them. Some are captured, displaced, and forced into entirely new lives. Some moons arrive with histories that begin somewhere else. Rather than forming beside the planets they orbit today, they appear to have wandered through the young solar system until gravity claimed them. Their presence reminds us that planetary systems did not always grow in orderly ways. They changed through encounters, close passages, and ancient upheaval that unfolded across millions of years. Scientists describe many of these bodies as irregular moons. An irregular moon follows an orbit that differs sharply from the large regular moons surrounding a giant planet. Its path may be unusually distant, strongly tilted, highly stretched, or even travel in the opposite direction from the planet's rotation. Those unusual motions suggest that such a moon did not form from the same disk of material that produced its neighboring companions. Capture offers one explanation. During the chaotic youth of the solar system, a wandering object could lose enough energy through gravitational interactions to become permanently trapped by a giant planet. Instead of continuing around the sun, it began circling a new master. The process is difficult and uncommon, yet the evidence appears across the outer planets, preserved in the remarkable diversity of their distant companions. Neptune provides the most striking example. Triton travels around Neptune in a backward orbit, moving opposite the planet's rotation. That unusual path strongly suggests capture rather than local formation. Many planetary scientists think Triton may once have belonged to a different region beyond Neptune before its fate changed forever. Its arrival may have reshaped Neptune's entire moon system, disturbing or even destroying earlier satellites that once occupied more stable paths. But the story reaches beyond Neptune alone. Jupiter, Saturn, Uranus, and Neptune each possess collections of smaller, irregular moons occupying distant and unusual orbits. Some travel together in loose families, hinting that larger captured bodies may have shattered after powerful collisions. Others remain solitary travelers whose origins are still debated. Every irregular moon preserves another fragment of the solar system's turbulent beginning. This matters because captured moons act almost like preserved visitors from forgotten neighborhoods. They carry clues about places we may never observe directly. Their compositions, motions, and relationships help scientists reconstruct episodes of gravitational disorder that shaped the architecture of the outer planets. Each orbit becomes a historical record written in motion rather than stone. As we begin seeing these systems together, the picture grows richer. A moon system is not always a peaceful family that formed side by side. Some members may be survivors of violent encounters. Others may have been taken from distant realms, while older companions vanished through collision or gravitational disruption. What appears harmonious today may conceal a history filled with theft, impact, and rearrangement that unfolded long before Earth itself became a living world. But not every mystery comes from where a moon originated. Some become unforgettable because their surfaces seem divided into completely different identities, as though a single world learned to wear two faces. At first glance, Iapetus seems to belong to two different worlds. As one of Saturn's larger moons, it circles far beyond the planet's brightest rings, carrying a surface unlike any other known moon in the solar system. One hemisphere appears remarkably dark, while the opposite side reflects sunlight with striking brightness. Even from great distances, the contrast is impossible to ignore. When we look closer, the puzzle becomes even more fascinating. The darker hemisphere occupies the leading side of Iapetus, the face that moves forward along its orbit. Scientists think this pattern began when dark dust from elsewhere in the Saturn system gradually settled onto that forward-facing surface. The coating itself may have started out relatively thin, yet, over immense spans of time, a powerful chain of physical changes likely amplified the difference. Temperature plays a central role. Dark material absorbs more sunlight than bright ice, causing those regions to become warmer. As surface ice warms, some of it changes directly into water vapor instead of melting into liquid. That vapor can drift through the moon's extremely thin surroundings before freezing again in colder locations. Brighter regions therefore gain additional ice, while darker regions lose more of it. This process steadily strengthens the contrast, allowing one side to become darker, while the opposite hemisphere grows even brighter. But Iapetus keeps another secret, stretching across much of its equator. A remarkable raised ridge follows the moon for a vast distance, reaching heights that astonished scientists after spacecraft observations revealed its scale. The formation resembles a gigantic wall extending across the landscape, although it is broken into separate sections rather than forming one continuous line. Its origin remains uncertain despite years of study. Several ideas continue to compete. The ridge may have formed through ancient tectonic activity, meaning large-scale movements and deformation within the moon's outer layers. Another possibility suggests material once settled along the equator from an early ring surrounding Iapetus before hardening into the structure we observe today. Other explanations involve changes during the moon's youthful evolution. None has gathered enough evidence to settle the question completely. That uncertainty is part of what makes Iapetus so memorable. We do not need extraordinary claims to appreciate its appearance. Natural, geological, and physical processes already produce a world that seems almost intentionally designed. The sharply divided colors, combined with the immense equatorial ridge, create patterns our minds instinctively search to explain. Yet, every careful investigation continues to point toward remarkable natural history rather than artificial construction. As we continue this journey together, Iapetus reminds us that nature often creates forms more surprising than imagination first expects. A moon can become deeply asymmetrical through ordinary physical processes acting over extraordinary lengths of time. But Iapetus reveals only one path toward becoming unusual. Titan shows another, where a dense atmosphere reshapes an entire world in ways that reach far beyond the surface itself. Not every world can hold on to the air around it. Across the outer solar system, many moons spend billions of years trying to keep fragile layers of gas against the pull of space itself. Their smaller size gives them weaker gravity than the giant planets they accompany, making it much easier for atoms and molecules to escape forever. The challenge never ends. Sunlight carries energetic radiation that can break apart molecules high above a moon's surface. Charged particles, tiny particles carrying electric charge, such as electrons and ions, stream through planetary environments and can gradually strip material away. Even when gases are released from ice or rock, they may linger only briefly before drifting into space. A substantial atmosphere is therefore an uncommon achievement among moons. But Titan stands apart. Saturn's largest moon possesses a remarkably thick atmosphere, one dense enough to hide the surface from ordinary visible light. Beneath that hazy sky, stable lakes and seas of liquid methane and liquid ethane collect in broad basins, while clouds form, rainfall occurs, and rivers carve channels across the landscape. It is a complete weather cycle, shaped by chemicals different from Earth's, yet governed by familiar physical principles. Titan reminds us that an atmosphere can transform the appearance and evolution of an icy world. Far beyond Saturn, Triton presents a different picture. Its atmosphere is extremely thin and composed mostly of nitrogen. As Neptune and Triton travel along their lengthy path around the Sun, changing seasons alter the balance between frozen nitrogen on the surface and nitrogen gas above it. Frost can change into gas, then later return to the ground as temperatures shift over time. Even a delicate atmosphere can respond to the slow rhythm of sunlight across decades. Io offers another variation. Its atmosphere remains extremely thin and constantly changing. Part of it comes from gases released by ongoing volcanic activity, while another portion forms when frozen material on the surface changes directly into gas under sunlight. The atmosphere expands and contracts as conditions vary, making it an active participant in the moon's surrounding environment rather than a permanent blanket. Many moons possess even less than this. Scientists use the word exosphere to describe an outer atmosphere so thin that individual particles rarely collide with one another before escaping or falling back to the surface. Instead of behaving like the dense air surrounding Earth, these particles travel long distances, almost entirely alone. As we continue exploring these distant worlds together, their atmospheres begin to feel surprisingly delicate. They are less like enduring oceans of air and more like temporary veils, appearing, fading, and changing under the influence of gravity, radiation, sunlight, and frozen landscapes. But once an atmosphere exists, even for a short time, chemistry begins to unfold. That chemistry is where the story becomes increasingly unsettling. Chemistry often begins long before biology enters the story. Across the outer solar system, scientists have discovered worlds where carbon-containing molecules form through entirely natural physical processes. This field is known as organic chemistry, meaning the study of carbon-containing compounds. The name can sound suggestive, yet it carries an important reminder. Organic chemistry does not automatically mean living organisms are present. Titan offers one of the richest natural laboratories for this process. High above its surface, sunlight and energetic particles interact with methane and nitrogen in the atmosphere, producing increasingly complex carbon-containing molecules. Over immense spans of time, these materials combine into a thick orange haze before slowly drifting downward. Grain by grain, this organic material settles across Titan's plains, dunes, lakes, and river valleys, becoming part of the landscape without any confirmed involvement from biology. But Titan is not alone in presenting intriguing chemistry. Material sampled from the towering plumes of Enceladus revealed organic molecules mixed with particles originating from its hidden ocean system. These discoveries show that carbon containing compounds exist within material connected to the moon's interior. They do not demonstrate living organisms. They do reveal that an important ingredient associated with life on Earth is present within an environment that continues to attract careful scientific attention. Europa presents another fascinating possibility. Its icy surface is constantly altered by intense radiation from Jupiter's surrounding environment. Those energetic particles can produce oxidants, reactive chemical compounds capable of participating in energy releasing reactions. Scientists continue investigating whether fractures, circulation within the ice, or other processes might transport some of these chemically useful materials downward into the concealed ocean beneath the crust. That connection remains uncertain, yet it represents one of the most important questions surrounding Europa today. The distinction between chemistry and biology becomes increasingly important as we continue this journey together. Life depends upon organic chemistry, yet organic chemistry itself can emerge through ordinary interactions between sunlight, radiation, ice, rock, and simple gases. Nature possesses many ways to assemble complex molecules without crossing the threshold into living systems. Complexity alone cannot answer the question we ultimately hope to understand. That is why researchers remain careful with every new discovery. No confirmed alien life has been found on Titan, Enceladus, Europa, or any other moon in the solar system. No confirmed biosignature, meaning an observation that can be confidently explained only by living organisms, has yet been detected. What scientists have identified instead are environments, chemical ingredients, and physical conditions that justify deeper investigation through future missions and more capable instruments. But that careful distinction has gradually reshaped one of humanity's oldest scientific quests. Rather than searching only for living organisms themselves, researchers increasingly search first for the conditions that could allow life to emerge. That shift in perspective has changed the direction of exploration, making every promising environment a place where new questions begin instead of easy answers. For generations, the search for life beyond Earth seemed to point in one direction. Mars captured public imagination with its dry valleys, ancient river channels, and minerals shaped by long vanished water. It was nearby, rocky, and familiar enough to picture ourselves standing upon it. As each mission returned new discoveries, we learned that billions of years ago, Mars possessed conditions that may once have supported habitable environments. That picture remains important, yet it gradually became larger. As spacecraft traveled deeper into the outer solar system, another possibility emerged from places almost no one had expected. Several icy moons appeared capable of holding liquid water today, protected beneath frozen shells that concealed entire oceans from direct view. Instead of searching only for worlds that were once habitable, scientists began asking where habitable conditions might still exist. But water alone does not complete the story. Living systems also require available energy and useful chemistry. On several moons, evidence suggests that these ingredients may still interact in the present era. Tidal forces continue flexing hidden interiors. Warm rock may meet buried oceans. Organic molecules have been detected in some environments, while other surfaces produce reactive compounds through intense radiation. Together, these discoveries reveal places where natural chemical processes continue instead of belonging only to distant history. Present-day environments carry special importance because they offer opportunities to observe active systems rather than ancient remains. A world that lost its favorable conditions billions of years ago can preserve remarkable evidence of the past. A world where water, energy, and chemistry continue today may allow future missions to examine processes that are still unfolding beneath layers of ice. That possibility has reshaped exploration priorities across planetary science. None of this diminishes the importance of Mars. Its rocks preserve an extraordinary geological record, and many questions remain unanswered. Venus also continues to challenge our understanding of planetary evolution through its dramatic climate and unusual history. Beyond our solar system, thousands of planets orbit distant stars, expanding the search into an immense cosmic landscape. Each destination contributes a different piece of the larger puzzle. But the discoveries among the moons changed the map in a profound way. Scientists no longer search only for landscapes resembling familiar continents beneath open skies. Increasingly, attention has turned toward hidden environments, buried oceans, enclosed seas, and places where thick ice conceals conditions that may never be visible from orbit alone. Habitability is no longer defined only by what exists on a surface. As we continue this journey together, the realization feels both hopeful and humbling. Some of the most compelling places to investigate may spend their entire existence beneath frozen crusts that hide them from ordinary view. The next great discovery may not wait upon an exposed plain beneath open sunlight. It may remain enclosed within darkness, protected beneath ice that has endured for immense stretches of cosmic time. But the most promising destinations are also among the most difficult worlds for us to reach. Long before a spacecraft reaches the surface of a distant moon, the greatest challenge has already begun. Every mission toward the outer solar system becomes an exercise in patience, engineering, and careful planning. As we travel farther from the sun, every success demands years of commitment before the first close observation can even begin. The journeys alone are immense. Missions to Jupiter and Saturn require many years of flight, often using carefully planned gravity assists, where a spacecraft borrows momentum from passing planets to gain speed without carrying additional fuel. But expeditions toward Uranus and Neptune become even more demanding. Longer travel times, greater costs, and fewer launch opportunities mean these distant systems remain visited only on rare occasions. Distance creates another problem. Sunlight grows steadily weaker across the outer solar system, providing far less energy for spacecraft. Large solar arrays can still operate under some circumstances, but they become less effective with increasing distance. For the farthest destinations, engineers often depend upon nuclear power systems that generate electricity from the natural heat released by slowly decaying radioactive material. Without dependable power, scientific instruments cannot continue their work. But surviving the journey does not guarantee success. Around Jupiter, powerful radiation fills enormous regions of space with energetic particles capable of damaging electronics and gradually degrading spacecraft systems. Protective shielding adds weight, while every instrument must withstand conditions far harsher than those encountered near Earth. Even carefully designed missions must balance scientific ambition against environmental risk. Reaching the surface presents another layer of difficulty. Many of the most compelling oceans may lie beneath ice that extends several kilometers, which is about 2 miles, below the visible landscape. A successful landing alone cannot immediately investigate those hidden seas. Future explorers may eventually require drills, melting probes, or entirely new technologies capable of descending through frozen shells while continuing to operate reliably in extreme conditions. Communication also demands patience from everyone involved. Radio signals travel at the speed of light, yet even light requires time to cross such enormous distances. Commands sent from Earth may take tens of minutes, and for more distant worlds, more than an hour, before arriving at a spacecraft. Every maneuver must therefore be planned in advance, because immediate guidance is impossible. Then there's the terrain itself. Cracks spread across icy plains. Jagged ridges interrupt otherwise level ground. Titan presents broad dune fields shaped by persistent winds, while frost and uneven deposits cover other moons with uncertain surfaces. Every landing site carries unanswered questions that only close observation can resolve. But exploration is restrained by more than engineering. Planetary protection guides how missions approach environments that could potentially support life. Preventing earthly microorganisms from contaminating these places helps preserve future discoveries and protects the scientific value of every observation. Together, these obstacles create a remarkable tension. Each moon reveals just enough to deepen our curiosity, then conceals the rest beyond the limits of present technology. That resistance is part of why every future mission feels like a doorway. Across the outer solar system, several new missions promise to deepen the story we have been following together. Rather than offering a single dramatic answer, each one is designed to collect thousands of careful observations, allowing us to understand these distant moons layer by layer. Every measurement has the potential to reshape ideas that once seemed secure. The National Aeronautics and Space Administration's Europa Clipper mission will conduct repeated flybys of Europa instead of entering orbit around the moon itself. Each close approach will examine a different region, gradually building a detailed picture of the icy shell, the evidence for the hidden ocean beneath it, the chemistry of the surface, and the moon's overall habitability potential. By observing Europa from many angles and at different times, scientists hope to understand how its visible landscape connects to the unseen world below. But Europa is only one destination. The European Space Agency launched the Jupiter Icy Moons Explorer mission to investigate Jupiter's remarkable family of icy satellites. Although it will study Europa and Callisto, its strongest emphasis falls upon Ganymede, the largest moon in the solar system. By eventually entering orbit around Ganymede, the spacecraft will explore its magnetic environment, interior structure, surface evolution, and the possibility that a deep ocean remains hidden beneath layers of ice. Far beyond Saturn's rings, another ambitious mission aims to explore an entirely different kind of moon. The National Aeronautics and Space Administration's Dragonfly mission is designed as a rotorcraft, allowing it to fly from one landing site to another across Titan's broad landscapes. Instead of remaining in one location, it will investigate many environments, comparing dunes, plains, impact features, and regions shaped by liquid methane. That mobility may reveal how Titan's unusual chemistry varies from place to place. Enceladus continues to inspire future mission concepts as well. Scientists have proposed spacecraft capable of flying repeatedly through its towering plumes, gathering samples from material naturally escaping the hidden ocean beneath the ice. Such missions could search for stronger chemical evidence, improving our understanding of whether the ocean possesses conditions favorable for increasingly complex chemistry. But some of the greatest opportunities still exist only on drawing boards. Orbiters sent to Uranus or Neptune would transform our understanding of entire planetary systems that have remained largely unexplored since brief flybys decades ago. Extended observations could reveal how their moons evolved, whether hidden oceans remain active, and how these distant families of worlds fit into the broader history of the outer solar system. What makes these future missions so important is the recognition that today's answers remain incomplete. Every existing model depends upon limited observations gathered across enormous distances. New measurements may confirm long held ideas, yet they may also overturn assumptions that have guided planetary science for decades. Each returning signal carries the possibility of replacing certainty with something even more valuable, a clearer understanding of how these remarkable moons truly work. The final movement of our journey now turns from worlds and missions toward a deeper question: what these moons reveal about our place within the solar system. Many of us first encountered the solar system through a simple picture. The sun stood at the center. Planets circled around it in neat order. Moons appeared as smaller companions, almost like decorations attached to larger worlds. Importance seemed to increase with size, while smaller bodies occupied supporting roles within an orderly cosmic family. That familiar picture serves as a useful beginning. It introduces relationships that are real and measurable. Yet, as our exploration expanded, the simplicity gradually dissolved. The farther we traveled, the more often the smallest members of planetary systems challenged the expectations we had carried since childhood. A moon can be larger than a planet. Ganymede exceeds the size of Mercury, even though it remains classified as a moon because it orbits Jupiter rather than the Sunday. Another moon can surround itself with a substantial atmosphere, as Titan does, supporting clouds, rainfall, rivers, lakes, and changing seasons unlike any other satellite we once imagined. Elsewhere, hidden oceans may extend beneath frozen crusts, isolated from open space, while remaining active for immense spans of time. But surprising comparisons continue. A moon can erupt with greater volcanic intensity than any planetary surface currently known, reshaping itself through relentless internal energy. Another can release towering plumes from beneath its icy shell. Others preserve ancient scars that record collisions stretching back toward the earliest history of the solar system. Each discovery reminds us that familiar labels rarely predict what a world will become. The deeper lesson reaches beyond astronomy itself. Human beings naturally organize nature into categories because categories help us understand an overwhelming universe. They create order where countless objects compete for our attention, yet nature follows physical laws instead of human expectations. Gravity, chemistry, temperature, pressure, and time determine how a world evolves. They pay no attention to the emotional importance we attach to words such as planet or moon. That realization changes the meaning of those names. Planet and moon describe relationships between bodies, not their destiny. A moon is defined by what it orbits, not by how complex it becomes. A planet is defined by its place within the solar system, not by an automatic promise of greater fascination. Once we separate classification from possibility, every world deserves to be examined on its own terms. You begin to notice a different pattern. Curiosity no longer follows the largest objects alone. Instead, it follows the places where remarkable processes continue, whether they occur beneath ice, within an atmosphere, across fractured rock, or inside oceans hidden from direct view. Size becomes only one characteristic among many, but perhaps the greatest change happens within us. We stop asking which worlds deserve our attention because of their names. We begin asking which environments possess the conditions that allow extraordinary stories to unfold. That shift replaces assumption with observation and hierarchy with discovery. Once we accept that, the search for life becomes more humbling. For generations, our search for life began with familiar expectations. We looked for sunlight warming a surface through long days. We imagined breathable air moving across continents. We searched for rivers, open oceans, changing seasons, and landscapes that resembled our own. The closer another world appeared to Earth, the more naturally we believed it deserved attention. Those assumptions came from the only living world we have ever known. They remain valuable, yet each new exploration has gradually widened the picture. Some of the most compelling places in the solar system no longer resemble the landscapes that first inspired our imagination. Instead, they hide beneath layers of ice, beyond thick atmospheres, or inside environments that seem entirely unwelcoming to us. But an icy moon can remain chemically active while sunlight barely reaches its surface. Another may appear completely frozen from orbit while liquid water moves far below the crust. Internal heat, produced through radioactive decay or the steady stretching caused by gravity, can preserve underground oceans for astonishing spans of time. Such worlds may seem lifeless from above, yet their interiors continue changing in ways that invite careful investigation. The same lesson extends further. A place may be deeply hostile to human exploration while remaining scientifically promising. Crushing cold, intense radiation, or frozen terrain do not automatically remove the possibility that useful chemistry continues beneath the surface. Human comfort and biological potential are different questions. We have learned not to confuse them. Earth itself offers an important reminder. Far beneath the oceans, entire ecosystems survive where sunlight never reaches. Organisms gather around hydrothermal vents, which are openings in the seafloor where heated, mineral-rich water rises from below. Rather than depending upon sunlight, these communities obtain energy from chemical reactions occurring within their environment. Their existence transformed our understanding of where life can persist. That discovery does not prove life exists anywhere beyond Earth. It proves something more careful and equally important. It expands the range of environments that scientists now consider worthy of exploration. The existence of chemical energy beneath Earth's oceans encourages us to examine hidden oceans elsewhere with greater curiosity, while remaining honest about what the evidence currently supports. A profound shift follows. Life may not require a world that resembles Earth when viewed from space. Instead, it may depend upon hidden stability, available chemistry, liquid water, and immense stretches of time working together beneath surfaces we cannot directly observe. Appearance alone tells only part of the story, but perhaps the most remarkable possibility is also the most humbling. Some of the most significant environments in our own cosmic neighborhood may exist where no human eye has ever looked directly. They remain concealed beneath ice, protected by distance, and revealed only through careful measurement and patient investigation. The ending returns to the image that has accompanied us throughout this journey: moons circling giant planets, carrying secrets through darkness. When we first learned the map of the solar system, the planets stood at the center of every lesson. Their names became familiar long before we noticed the worlds circling beside them. Those smaller companions seemed secondary, almost like footnotes surrounding the great planets. But as our journey has unfolded, that simple picture has slowly given way to something far richer and far more surprising. The planets still dominate the sky maps. They remain the great landmarks of our neighborhood around the Sunday, but their moons have become impossible to dismiss. Every new observation has revealed another world with its own history, its own geology, and its own unanswered questions. Instead of serving merely as companions, they have become destinations whose stories deserve equal attention. Some moons burn. Their interiors continue driving astonishing volcanic activity despite the immense cold surrounding them. Some flow. Hidden oceans move beneath shells of ice that appear completely frozen from above. Some freeze, Ancient surfaces preserve records reaching back across billions of years with remarkable clarity. Some hide. Their greatest secrets remain buried beneath layers that no spacecraft has yet penetrated. Some remember. Their landscapes preserve scars left by collisions, shifting interiors, and changing gravitational relationships. Some may even hold the ingredients that make the chemistry of life worth investigating. But that is why the title of this journey carries a deeper meaning. More terrifying than planets does not describe imaginary monsters or dramatic fiction. It describes worlds capable of overturning our expectations. They reveal environments more extreme than their modest size suggests. They conceal processes more active than their frozen appearances imply. They remind us that the surface we first notice may reveal only a small part of the complete story. As you reflect on these distant places, another perspective begins to emerge. Humanity is still standing near the beginning of this exploration. Only a handful of spacecraft have transformed our understanding so dramatically. A few brief encounters, lasting hours or days, have reshaped ideas that endured for generations. The missions still being prepared, and those yet to be imagined, may alter our picture once again in ways we cannot confidently predict today. The solar system no longer appears as a simple arrangement of major worlds surrounded by lesser companions. Instead, it resembles a landscape filled with mysteries of many different scales. Some tower across giant planets, others remain hidden beneath ice, beneath atmospheres, or beneath layers of rock that have never been touched. Importance does not always follow size. Discovery rarely follows expectation, but perhaps the most enduring lesson reaches beyond astronomy itself. We often overlook what appears familiar or small, only to discover that it carries the greatest capacity to change our understanding. The worlds once treated as supporting characters have become some of the most compelling places we know. And perhaps the most unsettling truth is this: the moons we overlooked for so long may ultimately become the worlds that teach us the most.